All right, let us talk about optimization. And I will say optimization is definitely something you will be doing in calculus, whichever calculus you see. Now, the process we're going to talk about really kind of specifically pertains to optimizing a quadratic function, because we know how to find where a parabola is biggest or smallest just by finding the y coordinate of the vertex. So that's what we're going to focus on. But there's still, aside from that, there's still a lot of other kind of things to think about when we're trying to optimize some situation. I guess we should read here. So optimization problems are word problems, which we've already kind of talked about last time, right? We want to be able to take words and make it into math, where we try to get the best of a given situation. The optimal solution may be the maximum or the minimum, depending on the context of the problem. And so we're going to start off with a very kind of classic first example of an optimization problem. Come on in. Ooh, we have a tattoo. Come on in. Let me see your symptom survey. Thanks so much. Sorry, you can take a seat right there. It's totally fine. Take a seat right there. Get it done. I will take a look at it once you have it. Notes. So optimization, we are going to do this problem where a farmer has 120 feet of fence. Well, technically linear feet, like when you talk about feet of fence, it's not like it's really square feet or whatever. Has 120 feet of length of fence. And they're going to build a rectangular corral for his animals. He wants to keep the horses and the cows separate for some reason. And the farmer needs a dividing fence. What dimensions would maximize the area for the corral? So when I'm doing an optimization problem, not always, but a lot of the time, the first thing I'm going to do is just draw a picture of the situation. So I'm going to make some little notes over here. First step is often to draw a picture. You guys can see that? Yes, you can see that. Wonder if I can move this around. Nope, sure can't. Okay. Draw a picture. There's an E picture, by the way. You know that? Yes. Okay. So I'm building a rectangular corral. And there's going to be a dividing fence in the middle. Great. Also, along with drawing a picture, we want to label the unknown things. And we're going to label them with variables. So I don't know how long any of the sides of this corral are. So I'm going to pick some variable names. I'm going to call this whole side here. Now, and there's different ways of doing this. Some people might call this length and this length the same thing. Like some people might call this X and this X. I usually make the choice when I do this problem to call this whole side a length of X. And this other side, a length of Y. You can use any letters you want. You can use L and W for length and width. You could use A and B, whatever, right? As long as you're not utilizing something that's already been used somewhere else, you're good to go. Now, it is important that the other side also get labeled. So this side also has a length of Y. This side also has a length of Y. This side also has a length of X. Great. The next thing I'm going to do when I'm trying to figure out how to optimize something is, what am I actually trying to optimize here? What do I want the most of? Do I want Y? So I want Y to be the most? Well, oh, so I know why you're saying Y. You're saying Y because we're talking about the vertex of the parabola thing, right? I think. So the thing is, I don't want just Y to be the biggest, because if Y was the biggest and I had like no X, I wouldn't have very much room for my animals. And the same kind of thing here, if X was the biggest and it had very small Y, there wouldn't be much room for the animals. So what's the thing I'm actually trying to maximize? The area, right? I want the most area. That's at least that's what the problem says, right? 120 feet of fence, keep the houses and cows separate. What dimensions would maximize the area? So that's what I'm trying to do. So I want to maximize area. So what I really want is an equation for the area. What's the equation for the area of this rectangle? X times y. And that's one of the reasons I picked that top side being a length of x instead of like x plus another x to make my area equation a little bit more typical. So typically the second thing we do is we write an equation for what we want to optimize. Right? You might be maximizing something, you might be minimizing something. Now, the issue here is that area depends on both x and y. It's a function of two different variables. And that's not something we have the tools to deal with. What we need to do is find some other sort of equation or relationship between those variables so that we can rewrite this area equation as a function of just one variable. So what we need to do is find a constraint. Oh, yep, I was just, yes, thank you. I know this. I think being zoomed in is good because you guys can actually see what I'm writing better, but the downside is I have to move around a little more. And that's all right. Do this actually. Cool. So we need a constraint. So the constraint is just some limiting piece of information. We know that the farmer only has 120 feet of fence to use. So all of the sides of the fence have to add up to 120 or less, but we really should use all of the fence if we're trying to get the most area possible. So our constraint here is, well, let's see, I've got y plus y plus y plus x plus x, and that should be less than or equal to, but I'm just going to say equal to 120. And really, we should make this look simpler. We're going to write it as 3y plus 2x equal to 120. Here's something I've noticed over the years that I think is worth remembering. The thing you're trying to optimize should never actually equal a number. Because you don't know what the most about, right? We're trying to find what the maximum area is. So we don't know what it is. So you should never be setting the area equation equal to a number. Whereas the constraint equation, which you're going to find in all these setups, is always going to equal some sort of number because you have some limiting piece of information. The reason I mention this is because over the years, I've seen a number of people write that the area is equal to 120 in a problem like this. Just be aware, right? The thing you're trying to maximize is just some function of the things you've got. The thing you're trying to, and then the constraint to be equal to a number. And I guess I should double check today. I should check your symptom survey if you've done it. And I won't put dots on this or she, he, either or. So yeah, we have a constraint, and then the next step is going to be to solve for one of the variables. Or if you prefer, we can say isolate one of the variables in the constraint. Sometimes it will be really obvious which one is easier to solve for, or which one is easier to plug back in for into the area equation, because that's what we're going to do. This one here, solving for x or y, it's pretty much the same amount of difficulty, so it really doesn't matter which way you do it. I'm going to solve for x. So 2x equals 120 minus 3y, and then divide both sides by 2. So that x is equal to 120 divided by 2 is 60, and negative 3 divided by 2 is negative 3 divided by 2. You can also say it's negative 1.5, but I usually prefer to keep things with fractions if I have the choice. You can use decimals though, that's also fine. Then we're going to substitute this back into the thing we're trying to optimize. So we're going to plug the rearranged constraint into the max min equation we are working with. Also, I will mention, right, all these notes are on Canvas. So if you don't get everything written down, and I'm writing a lot of things over on the side here, don't get it all down. It's okay. So we're going to take this and we're going to substitute it back in for x because we solved for x. So we're going to have the area is equal to x, which is 60 minus 3/2 y times y, which I'm going to multiply out. I'm going to distribute that y and say that area is equal to 60y minus 3/2 y squared, or writing it in the more kind of standard way we write a quadratic. Area equals negative 3/2 y squared plus 60y. So this is where the naming is going to get a little bit strange. This is a quadratic equation, right? If I graph this, I'd have to be a little bit careful, right? Because my input now is the y, and my output is the area. So if I was going to graph this, let me grab another piece of paper. I got like all the paper over here, all the paper over there. So just to back up for 1 second, if I was going to graph area equal to negative 3/2 y squared plus 60y, I would be saying the y's are on the horizontal axis and the a's are on the vertical axis. That's kind of the idea. I just want to point out, right? It's not always x here and y here. Sometimes we're thinking of a different letter as a function of another letter. If I was going to, I really kind of don't want to actually graph it, but it will. It's going to look something like this. It's going to be a parabola whose intercepts are 0, 0, and I don't actually know what that other one is. I don't really care what that other one is. What I really care about is what's that point right there? Because that point is going to be the y value of the vertex. Well, so right, this is where, again, the naming is a little bit terrible, right? There's my, I feel like I picked a better name for this, or not a better name, but like I feel like I did something slightly different before, but no, I really didn't. I'm going to call this, even though it's, I really don't want to call it Vy, but I'm going to. Right, that's what the input is. That's what the output is. So we're going to find the quote unquote x coordinate of the vertex, right? The input coordinate, the usual way. And then we're also going to find maybe the output coordinate. And those are going to represent what the y value is. So how long this part of the fence is. And that's going to represent what the area is. All right. So we'll come back to that a little bit. But I want to just kind of do the thing. So we know how to find the first, oh, that's what I was looking for, the first coordinate of the vertex, as opposed to the second coordinate of the vertex, let's say x and y. We're going to find the first coordinate of the vertex in the usual way. We are going to of the vertex is just going to be negative b over 2a, which is going to be, let's see, negative b over 2a is going to be negative 60 over 2 times negative 3/2, which is going to be negative 60 divided by negative 3, which is positive 20. And over here in the little instructions area, what we're doing there is we are finding the coordinates of the vertex. Well, I should really say find the appropriate. And this is kind of the time where you start going to think about what are they actually asking me to find? Right, because we've done this work, we're trying to maximize the area, but do they actually ask us to find the area? Well, let's go back and read the question. We look at the question. The question says at the end, what dimensions would maximize the area for the corral? So what we actually need to find are how long the y side is and how long the x side is. We already found how long the y side is. So what we're going to do is we're going to now, the last step is actually answer the question that's being asked. And when I say that, what I mean is read the question again and make sure. So we found the y thing, right? The y side is 20 feet long, but we still need to find the x thing. How long is the x side? And so what's typically going to happen is when you're finding the other piece of information they're usually asking you to find, you should go back and look through your work, because somewhere in your work, there should be an equation of the thing you want to find. We're trying to find x. Oh, look, there's an equation where x is already isolated. So we're just going to say, excuse me, x is 60 minus 3/2 times y. But we just found that y was equal to 20. So x is going to equal 60 minus 3/2 times 20, and 3/2 times 20 is 3 times 10, which is 30. So we found the dimensions of the corral that maximize the area and fit all the requirements. We're also going to look at the graph because I think it's worthwhile, but before we do that, questions? Yeah. Oh, yeah. I know, like, I really debated just turning that off. And actually, you know what? Well, I don't know. I just feel like it's weird. Like, did you watch the video later? No? Okay. I mean, it feels weird to be this disembodied, like, I'm just a hand and I'm talking. But there's no one on Zoom, so I feel like I can totally turn that off. Oh, there is? Oh, I was looking at the chat, not the, yeah, okay. I mean, not for the Zoom, right? Hey, people on Zoom, sorry, I didn't see you there. Apologies. Not to discount you. Right. So we'll keep the picture. We can handle it. Where's another hand too? Yeah.
Why we should write the dimensions?
Yes. So we should definitely say, and I kind of ran out of room, but I would say my final answer is x equals 30 feet, y equals 20 feet. It is important to include the appropriate units in our final answer. I feel like I saw one other hand somewhere, but maybe I'm just kidding. Let's go look at the graph of this thing for the not the full graph, but I want to show you the graph just because there's one or two things I want you to see. So what we found that the y coordinate, the first coordinate of the vertex, right? We found our negative b over 2a value to be 20. And that's what was going right there. And then if you did find the second coordinate of the vertex, well, let's see what we get. If I plug in 20, I'm going to get, let's see, negative 3/2 times 20 squared plus 60 times 20. That's going to be negative 3/2 times 400. 60 times 20 is 1200. Negative 3/2 of 400 is negative 600 plus 1200, which is 600. What is that amount representing? It's not the x value. It's the area, right? It's 20 times 30. It's what the area actually is. So typically, if you decide to take the time to find the second coordinate of the vertex, what you're typically finding is the maximum value of the thing that you maximize, or the minimum value if it's the minimum value. Right, but this question didn't actually ask us to find that. We could also have said, oh yeah, by the way, and the maximum area is 600 feet squared. We also could have said that after we found x and y. Right? So we know x is 30 and y is 20. 30 times 20 is 600 square feet. But I just want to point out, right, this second coordinate of the vertex is not the other dimension you're trying to find. So don't find this if you don't need to. right? I'm always about don't do the work you don't need to do. Right? If they're asking me to find the area, if they were asking me to find the area here, I'd probably still go back and find the other dimension x and then just multiply them together. I feel like that's probably actually easier. But you can do it whichever way you want. All right, let's look at another problem. Here's my thumb tool. Skip the terrible blank page that you might have and go to the next one. Note, this question comes directly from the Math 16 textbook that they used it. The company has determined its total revenue in dollars using the product to be modeled by R equals negative x squared plus 450x plus 52,000, where x is the number of units produced and sold. What production level would yield the maximum revenue? What is the maximum revenue? This problem is actually a little bit easier than the previous one did because they're already giving us a lot of the information that we need, right? We're not having to set things up. So let's go through our steps. There isn't really a picture to draw here. I mean, we could draw the parabola if we wanted to, but we don't really need to. There's no picture that's kind of describing the situation. But we're trying to maximize, right? We want to maximize the revenue. Negative x squared plus 450x plus 52,000. We don't need to look for a constraint here because the thing we're trying to maximize is already a function of one variable. Right? The previous problem, we definitely needed to look for a constraint. Sorry, I'm trying to keep track of where I put my graph. Okay, I'll find it later. It's fine. But the previous problem, right? We needed to look for a constraint because area was a function of x times y. Here, r is already given to us as a function of x. So really, we just need to go find the coordinates of the vertex, right? We don't need to solve the constraint. We don't need to plug it back in. We just get to skip ahead and say like, all right, I want to find the first coordinate of the vertex. Which is the x coordinate here, but it's going to be precise. So again, I want my negative b divided by 2a, and that's going to be negative 450 divided by 2 times the negative 1. Which is going to be 225. 225 what? What is this actually representing? Well, it is what the x value is, and x is, sorry, it's off the page, I know. X is the number of units produced and sold. So we are producing 225 units. I should ask a different question, actually. How do you know it's going to be a maximum? Right, exactly, because our parabola is doing this. It's opening downwards. We know we have a vertex that's at the top, not at the bottom. So they've asked us to find the production level. We did. So we answered part 1 of it. We're going to produce 225 units. But we also want to answer what's the other coordinate of the vertex, because that's going to represent what the revenue actually is. So we need to plug that back in. So if x equals 225, what is the revenue? Well, we have the equation for that. The revenue is negative x squared plus 450 times x plus 52,000, which is maybe not the nicest math ever. My 225 squared is not a number any of us should know off the top of our head. I mean, if you do, great, excellent, but I don't. I have written it down though. That's going to be, so remember, when you have a negative something squared like that, it's the thing squared first and the negative after. So it's going to be negative 50,625 plus 101,000 250 plus 52,000. It is notable that this number is half of that number. In fact, that always happens. When you find the y coordinate, the second coordinate of the vertex of a parabola, this is always true. So if you're finding specifically the second coordinate of the vertex of a parabola, and you plug it back into your ax squared plus bx plus c, the first thing and the second thing always have two features. They're always opposite signs, and the first one is always half the second. Always true. Think about some of the other examples we've done. Like when you're on your own sometime, look at maybe, x squared plus 6x plus 5. In fact, let's just do it real quick. The x coordinate is going to be negative b over 2a, which is negative 6 over 2, which is negative 3. And you plug in negative 3, you get 9 minus 18. I don't care about that really. But that's half of that, and they're opposite sides. Always true when you're finding the second coordinate of the vertex. Good, yeah. So what I'm trying to say here, if this is half of that and they're opposite signs, when you add them together, negative this plus that is just going to be 50,625 plus another 52,000, and then we add those together, and we get $102,625. That's the maximum revenue. Yep, thank you. And if you were to graph this, we got a little bit of room here, not a lot of room. I don't know exactly what it would look like, but it would look something like this, where this is the horizontal axis is the x-axis, the vertical axis is the y-axis, sorry, it's the r-axis. And that vertex there is the point 225, comma, 102,625. Yes?
Why did you leave the negative sign there?
I didn't. So I see why, but I know you think I did, because look at that. What I did was I added these two numbers together.
Oh, okay, sorry.
Yeah, no, you're excellent question. It definitely looks like I just popped off a negative sign there, but really I did negative this plus that, and then there's still the 50,000 there. All right.
And is that rule about like the half and opposite signs, is that just for the second coordinate of the vertex?
Yeah, so if once you found the negative b over 2a part, then when you plug that back in to find the second coordinate of the vertex, it's always going to happen like this. It's just something I've noticed over the years, right? Oh yeah, this always happens, and it is true. I thought about it, and I did the thinking that you need to figure out why it's actually true, but it's totally true. It's kind of neat. If you really wanted to spend some time thinking about it, you could take a very general expression, ax squared plus bx plus c, and ask yourself what happens when you plug in negative b over 2a for x. You should see that when you do that, these first two terms, this one's exactly going to be half of that one, and they're going to be opposite signs. You don't have to do that though, but if you want, if you're bored and want some math to do. Yeah. I know that's what you all do with your free time when you're not doing other exciting things. Oh, I should do some math. Yeah. So find the dimensions of the largest rectangle by area in the first quadrant that can be inscribed under the line y equals 18 minus 6. And it will just say generally, when someone says find the biggest thing, they usually mean the biggest of its kind of largest dimension. So if I said find the biggest sphere, we mean the sphere with the most volume. If I said find the biggest circle, we mean the circle with the most area. So whatever its kind of biggest dimensionality is what you're trying to maximize when they say find the biggest one. So let's draw a picture. We want the largest rectangle in the first quadrant to be inscribed, meaning it fits under the line y equals 18 minus 6x. So y equals 18 minus 6x, The line does something like that. If it has a y-intercept of 18, if it has an x-intercept, let's see. 18 minus 6x equals 0 because we set y equal to 0. 18 equals 6x. X equals 3. So there's my x-intercept at 3, 0. And what we're trying to do is we're trying to inscribe a rectangle. So maybe a rectangle looks like this. Now, that is definitely not the one that has the most area, right? Because I definitely could have pushed it further to the right or further. So if you're trying to draw the rectangle with the most area inscribed under this line, its corner should really touch the line. You should use all of the space you've got, meaning it probably looks something more like this. Now again, I don't know. A question.
Just to clarify, the first quadrant is the positive x and y.
Exactly. Yeah. So when you talk about the quadrants of the coordinate system, the first quadrant is the upper right quadrant. It's where x and y are both positive. And then the numbering just goes counterclockwise. So first quadrant, second quadrant, third quadrant, fourth quadrant. We will definitely talk more about when we get to the trig part of this class, where we really talk about the quadrants a lot. So I don't know how wide or how tall this rectangle is. If I did, I would know what its area was. We're trying to maximize its area, so we don't know what those things are. So we're going to give them variable names. I'm going to call this x. I'm going to call this y. And the reason I'm specifically normally I would just say choose whatever, but in this kind of picture, I'm thinking about like using the regular graphing system and x being the horizontal and y being the vertical. So I can think of this point here as the point x comma y. And that's my first step. Second step, what am I trying to maximize? Right. So maximize area, and area is equal to x times y. So now we need a constraint. And I think we can all physically see that the constraint is that the rectangle has to be under that line, right? We are definitely limited in how big the rectangle can be. But we've been kind of a little bit more specific. Not only does it have to be under the line, we have drawn it in such a way to get the most possible area. We want one maximize. We want that corner to live on that line. Right? That's going to get us the most area. But if that corner lives on that line, we know a relationship between x and y. Because if you're on this line, well, that line we know the equation of. So that line equation is actually our constraint. We are constrained by the fact that y has to equal 18 minus 6x. And that's something that happens a lot, right? If you're trying to do a optimization problem and you have something that gets stuck on a graph that you already know the equation of, that graph is typically what is your constraining piece of information. We'll see more. We'll see another example like this. I think that's what our next example is. Yeah, definitely. Yeah. So that's kind of the idea. We'll do another one to kind of help drive home the point. Yeah, we got time. Okay. All right. We've already solved for y here. Great. Let's plug that into the other things. So I'm going to then. Thank you. Yes. Right. We already solved for y. Step 5, plug it back in. You don't have to number your steps. I'm just trying to kind of be very, like, if you wanted to look back and see what all the steps were, you could follow along. But you definitely don't need to, probably shouldn't label your steps. You be like, I'm doing the thing, and then the next thing, and the next. We're going to area equal to x times 18 minus 6x. And then I want to multiply it out. So area is going to equal that, thank you, 18x minus 6x squared. And then I do recommend rewriting it so that the highest power of x comes first. Just because there definitely were a few of you that did, like there was, I think, one question on the previous homework, it was like 4x minus 3x squared, and you had to find the vertex. And a number of you did get the a, b value switched up because it was written out of order. Just remember that the a value is always the coefficient of x squared, even if it's written over there. And the b value is always the coefficient of x. Even if you put it first. So now I want to find the vertex. And in this case, the x coordinate of the vertex is the normal first coordinate. So I'm just going to use the normal notation and say that the x coordinate is negative b over 2 times a, which is negative 18 over 2 times negative 6, which is, I might just cancel a 2 right away and say it's negative 9 over negative 6. I should probably make that positive. Positive 3/2. So the x value that's going to give us the most area in our rectangle is 3/2. Are we done? Did we answer the question? What did they ask us to find? The dimensions. So we found the x dimension. We still need to find the y dimension. Now, I will note here they didn't actually give us any units, right? They didn't say like this triangle was, intersecting the x-axis at 3 feet and intersecting the y-axis at 18 feet. It's just so you don't have to provide any units here is what I'm pointing out. If they're just giving you the shape and they didn't say there were any units, you don't have to worry about units. But we do have to worry about finding the other dimension. So we still need to find y. Luckily, we have an equation for y right there. So y is equal to 18 minus 6 times 3/2. And that's going to give you 18 minus, let's see, 6 times 3/2 is 3 times 3, which is 9. That's going to give you 9. So those are the dimensions of the rectangle that maximize the area. I will just point out an observation is that whenever you have a question like this specifically, where you have a line and a rectangle underneath it, the coordinates of the dimensions of the rectangle always end up being half the intercept values. So our intercept values were 3 and 18, and our length values were half of 3 and half of 18. Something that occurs quite often. They didn't ask us to find the area, so we're not going to find the area. But we totally could find the area just by multiplying x and y together. Or if you really wanted to, and I really should, actually, this is a perfect time to say it, right? If you found the y coordinate of the vertex, so if I plug that 3/2 back into the parabola, to the quadratic, negative 6, whoops, I need the 6, times 3/2 squared, plus 18 times 3/2 is going to give me, let's see, negative 6 times, let's see, 3/2 squared is 9/4. 18 times 3/2 is 9 times 3, which is 27. Negative 6 and 4, I can cancel a 2 there and a 2 there. So I have negative 27 over 2. So look, again, we're seeing the same thing, right? I'm getting negative 27 over 2 plus 27. The first thing is half the second thing, and they're opposite signs. So negative 27/2 plus 27 is just positive 27/2. That's not the y value we found though, right? Because it's not the y value, it's the area. So I just want to make it really, really clear. If you're finding like x and y, if you think about the parabola, this parabola isn't y as a function of x, it's a area as a function of x. So that there, it might be better, instead of calling it vy, it might be better to call it VA. I'm not saying you have to find this because this question didn't ask us to find it. I just want to make it really, really clear that when you find this thing, you're finding the value that is the maximum value of the situation. Right? This rectangle has a maximum area of 27/2. It has dimensions x equal to 3/2 and y equal to 9. So just be careful. Make sure you think about what you're really being asked to find and try to find what you're being asked to find. All right, let's do the next one. The last one. We'll do more of these on Friday. Oh, there's my graph. Okay, I didn't go. I want to put that out. So, well, thank you. Yeah. Which point on the line y equals 3x plus 1 lies closest to the point 2, 0? Okay, let's draw a picture. Try and draw an all right picture here. So y equals 3x plus 1. It doesn't need to be perfect, right? I know that has a y-intercept of 1, has an x-intercept of -1/3. I don't really want to draw it that close to the origin, so I'm going to maybe scoot it over a little, maybe not quite as perfectly -1/3 as it needs to be. That's okay. Now I want to find the point on this graph that is closest to the point 2, 0. So 1, 2. So there's some point on this graph. I don't know what it is, right? We're trying to find it. But there is a point. I'm going to pretend like it's right here that is closest to that point there. So if that is actually the closest point, oh, by the way, I'm going to label it x, y, because I don't know what it is. But if xy is the point that's closest to 2, 0, what should be true about the distance between them? Is it big or is it small? If it's the closest point, right? It's as small as possible. Or in other words, we need to minimize the distance between the 2 points. If you're ever trying to find a point that is closest to another point, what you're really trying to do is minimize the distance between xy and 2, 0. That's what we're trying to do. Or I guess what we're really trying to do is find the point that does that, right? We're trying to find the point xy that minimizes the distance between them. And we know what the distance formula is. The distance between 2 points is the square root of x minus the x coordinate squared plus y minus the y coordinate squared. And there's something I should tell you now. Minimizing the distance is fine, totally works, but you might realize or notice there's a square root there. And if we graph that square root thing, or we think of it, it's not going to actually be a parabola, which is fine later on, but currently the only way we can really find if a function has a maximum or minimum is by finding the vertex of the parabola. So it kind of needs to be a parabola to be able to find its maximum. But here's the thing. If I want to make this distance as small as possible, well, if you take the square root of something, the way to make the square root of something as small as possible is to make the something as small as possible. Right? If you make the inside small, you make the output small, because the square root of a function is what's called an increasing function. Right? As the inputs get bigger, the outputs get bigger. As the inputs get smaller, the outputs get smaller. So all we have to do is make the input as small as possible. In other words, instead of minimizing this, we're going to minimize the insides. X minus 2 squared plus y minus 0 squared. And it will achieve the same result. And this is something you should carry with you in future classes. If you're ever asked to maximize or minimize the distance between two things, it is always an option to minimize the insides. Or in other words, people also say it is minimize the square of the distance, because that's what we've done, right? We've squared the whole thing to get rid of the square root. That is always a valid technique to do. So you should definitely use it in the future, because you will be asked to do this. So we want to minimize that, but now we're back in this thing where we have more variables than we want. Again, x and a y. I don't know how to draw that parabola. It's not a parabola yet. I needed a constraint. And the constraint here, like the previous problem, is that that point xy has to be on the line. Right? We're trying to find the point on the line that is closest to this other point 2, 0. So our constraint is y equal to 3x plus 1. And we're just going to substitute that in for y. So now we're trying to minimize x minus 2 squared plus, instead of y minus 0 squared, it's going to be 3x plus 1. I'm not going to write the minus 0. Right? Minus 0 doesn't change anything. We're trying to minimize that. Okay, so now we're just going to simplify it. So let's multiply it out. So be careful, when you multiply out x minus 2 squared, there's a middle term, it's x squared minus 4x plus 4. And 3x plus 1 squared is going to be 9x squared plus 3x plus 3x, which is 6x, plus 1 squared, which is 1. All I'm doing there, right, is I'm saying that this is, x minus 2 squared is x minus 2 times x minus 2, which I FOIL it out and get x squared minus 4x plus 4. And 3x plus 1 squared is 3x plus 1 times 3x plus 1. And when you FOIL all that out, you get 9x squared plus 3x, which is 6x plus 1. And now, so I've done something which is fine, but I feel like I should fix it a little bit. Usually when we're maximizing or minimizing something, it's kind of equal to something else. So normally what I say is we're not minimizing the distance, we're minimizing the distance squared. I would usually write that on there. Usually you want some name for the thing you're maximizing and minimizing. So I should probably be like, okay, this is the distance squared. This is the distance squared. It just feels weird to not have like something equal to the thing you're optimizing. It's okay if there isn't though, really. Let's simplify this. The distance squared, so x squared plus 9x squared is 10x squared. Negative 4x plus 6x is 2x. 4 plus 1 is 5. Great. Now we're back in the parabola land that we love. We can have a parabola, we can find its vertex, good to go. So let's find the x coordinate of the vertex. Thank you. Yes. Always. Negative b over 2a is going to be negative 2 over 2 times 10. 2's cancel, and we get negative 1/10. So the x coordinate of the vertex, or the x coordinate of the point that we're trying to find, is negative 1/10. We were asked to find the point on the line that's closest. Look back over here for a second. Which point on the line, y equals 3x plus 1, is closest to the point 2 comma 0. So all we have to do to find the other coordinate of the point is plug back in x equal to negative 1/10 into our constraint right here. So we know that y equals 3x plus 1, and then we're just going to plug in x equal to negative 1/10 to get y equal to 3 times negative 1/10 plus 1. 3 times negative 1/10 is negative 3/10. 1 is equal to 10/10. Good. And then negative 3/10 plus 10/10 is 7/10. So the point on the line, y equals 3x plus 1, that is closest to the point 2 comma 0 is negative 1/10 comma 7/10. And we were not asked to find the distance between them, so we're not gonna find the distance.